Hi, I'm Elizabeth, and I'm going to be talking about Lab 1, which is all about charge tapes. Just an overview of this presentation. I'm going to start with an introduction, which includes talking about the fundamental principles and description of the lab, and then I'm going to go into the experiment and its procedure, and then I'm going to talk about the observations and data, which includes data collection and measurements with some interpretations, and then I'm going to go into my GlowScript code, which is a computational model of two charge tapes exerting electric force on each other, and then I'm going to do discussion and conclusion, and also answer the what if and why questions. So some of the fundamental principles we used were Newton's second and third laws, also the formula for electric fields, which is equal to E equals kq over the distance squared times the unit vector of the distance, and then also Coulomb's law, which is the same thing as k times q1, q2 over r squared, or it's also the electric field times another charge. And then we also talked about the force due to gravity, which is, of course, F equals mg. And then a quick description of the lab. We created charged sections of Scotch or clear tape, and then following the observation of the tape's interactions with each other and with other objects, we are going to estimate the amount of excess charge on a single piece of the charged clear tape. So a quick preview of my results: that I determined the pieces of tape exhibit a positive charge, and they are drawn towards a pen that has a negative charge, and the tapes also demonstrate repulsion from each other. So some assumptions I made was that I'm going to treat the tape as a point charge, where all of the charge is located at the center of both pieces of tape. Both tapes also have the same amount of charge, and air resistance is going to be negligible. So the procedure for our experiment was we were going to form two U-shaped tape segments and quickly detach the U-shaped tape from the base tape. And then to ensure that the tape had a negative charge, I rubbed a plastic pen on my clothes and positioned it near the tape. And then I'm going to repeat that process for the second piece of tape. And then I hung one of the charged tapes between two objects of identical height. I used textbooks. And then I positioned the other tape beneath the suspended one. And then I noted the distance between the tapes once the upper tape began to float. So some of the observations I had. And here's a quick look at what the experiment looked like. And then, of course, tape A is the surroundings and tape B was the system. Some of the interactions I observed were that the tape and the hand had an attractive force. Both pieces of tape had a repulsive force. The tape and the books had an attractive force, and the tape and the negatively charged pen had a strong attractive force. And so using that, I determined that the tapes were positively charged. Some of the hand calculations I did, I measured at the length of the tape, the width of the tape, and the measured distance between the tapes. And then I used that to calculate the tape's weight, which is the same thing as the force of gravity. I also calculated the surface area of the tape, which I then used to find the number of atoms in the tape, which was 6.23 times 10 to the 17 atoms. So then I used the force of gravity on the tape, which I already calculated. I drew a free body diagram, and I determined that the sum of the forces in the y direction was going to be equal to 0, so that therefore the electric force was equal to the negative of the gravity force. And then I used Coulomb's law, rearranged it a little bit, and found that the charge on each piece of tape was 9.82 times 10 to the negative 7 coulombs. And then I calculated the excess electrons on each piece of tape by dividing by the charge of an electron, and I got 6.14 times 10 to the 10 excess electrons. And then the ratio of excess electrons to atoms I calculated was 9.86 times 10 to the negative 8 electrons per atom. So then I did some coding where I put in the fundamental constants and some of the stuff I had already measured. And then I used some equations from class to do some calculations where I could print the charge on each tape, the number of electrons on each tape, and the ratio of electrons per atom. And then here I did the objects where I was able to do a visual representation of the vectors, which we can see right here. And I also found that the output of my calculations was the exact same as my hand calculations, which was great. And so then here's some questions. What if electrons had positive charge and protons had a negative charge? So if the signs of the charges of the electrons and protons were to flip, then the direction of their electric fields would also flip, because that is included in their equation. And then all the calculation signs would also flip. But since the magnitude of the charges would remain the same, the behavior of the tapes would not change. It would still be the same as the earlier experiment. And then why is it important to handle the charged tapes as little as possible? We need to keep the tapes as positively charged as possible to observe significant results and reduce human error, because my hands and other objects have negative charge, and if it touches the tape, it's going to polarize. So in conclusion, objects with the same charges repel and objects with different charges attract, basically. And when no other forces are acting on the tape, we can determine that the electric force on the tape is equal to the force due to gravity. or the negative of the force due to gravity. We can use Newton's second laws and third laws, as well as Coulomb's law, to find the charges of everyday objects, which I thought was pretty cool. And then some of the possible sources of error for my experiment was human error, of course, and some of the assumptions we made, like neglecting air resistance. And that's it.